Do I have this on right? Okay, it's working. All right, that's fine. All right, I guess we'll get started this morning. Good morning, welcome. I wasn't here for, hi, thank you for waving. I wasn't here for part of yesterday morning, so just want to introduce myself. My name is Sylvia. I am currently working in Germany as a postdoc. My background is in gamma ray bursts and high energy observations. So in my PhD, I worked on gamma ray data from a satellite, the Fermi Gamma Ray Space Telescope, and all the sort of things that come with that. And now as a postdoc, I work on searches for continuous gravitational waves. So you might have all heard, you've all definitely heard and done much math, I think, and written code about the gravitational waves from binaries that merge. So I'm going to be talking a little bit later about something slightly different. I should say, let's see, I'm not sure how long this will take. I don't think I have enough material, which is okay. I think we can spend a lot of time discussing. I want you guys to ask questions. Obviously it's easy to say, right? Easier said than done. But I especially want you to ask questions because there's a lot of things that I don't know. There's a lot of things I think that any of us don't know. And so I think it's important to ask questions and make sure that we all understand what's happening. So with each slide or with each sort of set of slides, make sure you understand what's going on and if things make sense to you. If something doesn't make sense, just raise your hand and say that doesn't make sense because maybe I've explained it poorly or maybe I have something wrong up here. So I've also realized that I don't actually have my name up here, which is fine because if the talk goes poorly, then I'm just not going to write my name up there, or I'll write Daniel's name. It'll be fine. If the talk goes well, I'll put my name on there. So we're going to talk about gamma ray bursts. I'm going to focus on sort of an astronomy or astrophysics standpoint. This is what I used to do. I studied sort of gamma ray burst observations, or observationally. So I think everyone here comes from a slightly different background, right? Some people come from a very pure physics background. Some people come from more of an astronomy, observational background. I've tried to limit the amount of astronomy jargon in here, but if you find that there are words you don't understand, just ask, because a lot of times, right, like in any language or any sort of specific topic we talk about, there's going to be very specific words that are just used by that topic that other people don't use. And so I think it's important to make sure we understand what's going on, like a parsec. I mean, we've all heard parsec, right? But who knows exactly what a parsec means or where that comes from? Yep, go ahead. Computer guy? What's a parsec? Yeah, exactly. It's a unit of length, about 3 light years. I didn't quite hear. Could you speak up a little bit more where that comes from? Or where exactly the idea of parsec comes from? Exactly, yeah. Yep, excellent. So, yeah, exactly. So, a lot of terms in astronomy come from historically, right, back in the day when we didn't have these big telescopes and things, all people could do was just see what they could see with the naked eye, right? And so how could you measure how far away something if you don't have a telescope, if you can't measure redshifts and things like that? So what people used to do is they'd say, all right, here is the sun, here is the Earth. So at some point, at one point during the year, the Earth is over here. On the other side of the other halfway through the year, the Earth is over here. And you have sort of a fixed background of stars up here, right? So the stars that are really far away, they never seem to move. If there's something that's over here, if a star is closer to us than the fixed background, when the Earth is over here, you look for that star and you say, all right, it's somewhere over there. On the other side of the orbit, the Earth is over here, and so you're going to say, okay, that star seems to have moved. It seems to have gone from here to there. And so what a parsec is, all it is, so there's this distance over here, 1 astronomical unit. It doesn't matter, this is more jargon. So all a parsec is how far away is this? How far away an object is from the sun or from us in order for it to seem to move by 1 arc second over the course of a year or half a year. So if that was boring, if you guys already knew that, sorry, just wanted to make sure we're all on the same page there. So we're going to talk a little bit about gamma ray bursts, and we've heard a little bit, I think, about. I assume that probably gamma ray bursts. Yeah, gamma ray bursts have been mentioned. GRBs have been mentioned. So GRBs were discovered completely by accident. We were not expecting this. In the 60s, there were a bunch of satellites that went up. Well, the 60s were a troubled time. A bunch of satellites went up to make sure to sort of monitor the sky for signs of nuclear testing, let's say, hidden surprise nuclear testing. This was, around the Cold War and such. And some of these satellites, so they were looking for signs of nuclear testing. And so they were designed to observe very high energy events, so X-rays, gamma rays. And by accident, a handful of them saw these bright flashes in the sky. And when they looked at these bright flashes, they said, all right, well, they don't seem to be coming from the Earth, and they don't seem to be coming from the sun, and they don't seem to be correlated with any other bright flashes that we know of, because we knew of supernova and things like that, and they weren't correlated with supernova. So then the question became, what are they? What exactly is going on here? And it took a while before enough data came in. So this is sort of how astronomy works, right? It takes a while for enough data to come in for people to figure out what's going on. And before people could start figuring out exactly what is going on, exactly what are gamma ray bursts. So now comes the question, what exactly is a gamma ray burst? Right? Literally, it's a burst of gamma rays, but it's not that any burst of gamma rays is a GRB. A GRB refers to something very specific. So you have a bright flash of gamma rays, that's fine, but this bright flash could last anywhere from less than a second to hundreds of seconds. So that's already kind of weird. It's lasting for a very long period of time, and a lot of these light curves look different, right? Some of them just have one peak, so you just have one event that just slowly fades away over time, that's fine. Others have a lot of bright peaks right next to each other, that's fine. Some of them have sort of some of them have one emission episode and then a lot of quiet and then another emission episode after that. So this is sort of what I was talking about, or we were sort of discussing yesterday in the afternoon, that GRBs intrinsically look different, right? They're not like supernovae or maybe, certain types of stellar activity where if you've seen one, you can kind of extrapolate to the rest. GRBs intrinsically look different. So what you get is a bright flash of gamma rays, and then a lot of times, but not always, a lot of times you get sort of this long-lived fading emission at longer wavelengths. So what you're seeing here at the top is a bunch of different X-ray light curves. These are afterglow light curves. So there's something happening where you have a bright flash of gamma rays, and then sometimes you have X-rays starting up here and then slowly fading. And you notice they all kind of, they all kind of have a similar pattern, but some of them rise up a little bit, some of them just drop more quickly. So that's the top. And at the bottom, what's plotted is the optical light curve. So some of these GRBs also have optical emission, not all. So this is part of the problem of astronomy. If we don't see optical emission from all GRBs, is it because not all GRBs intrinsically will have optical emission, or is it because for some reason we just didn't observe it because it was pointed in the wrong direction or in the wrong, maybe it was too far away? So after a while, and this took a couple generations of detectors, because the first detectors that went up, the first gamma ray detectors that went up, they were testing for nuclear activity, and they couldn't necessarily tell you exactly where on the sky something was. And so it took a couple generations of gamma ray detectors before we finally got a good idea of what was going on and where gamma ray bursts were coming from. Because the first question is, are they coming from inside the solar system? Are they coming from inside the Milky Way? Are they coming from outside the Milky Way? How far away are they? And so what was happening is people started to notice that they were coming from all over the sky. If they're coming from all over the sky, they're either really close to us or they're really far away. And long story short, they're really far away. They're outside our galaxy. Actually, this is fun. Okay, I remember learning back in the day that the dinosaurs and other extinction events, when the dinosaurs died, all the extinction events were caused by, asteroids hitting the Earth and things like that. There's one extinction event, the KT extinction event, I think, that might have been caused by a gamma ray burst. It's a little uncertain, but what happens is when a gamma ray bursts, like let's say, a GRB hits the Earth. By hits the Earth, I just mean we get a lot of gamma rays at once, right? And it's not going to happen anytime soon, it's fine. But if a lot of gamma rays hit the Earth, that deposits a lot of energy into the Earth, and that starts affecting things like the atmosphere, and it starts to turn some of these nitrogen and oxygen molecules into things like nitrous oxides, which I think it's nitrous oxides. If anyone is a chemist in here, I apologize for getting this wrong. But basically, it starts to turn the atmosphere into something that's browner and more opaque, and then it sort of And then it sort of leaves kind of imprints because you have these different, these different chemical composition now. It sort of leaves an imprint on the, let's say, the soil and the trees and things like that. And so there's an idea that maybe some of these extinction events have been caused by gamma ray bursts. So yeah, I mean, this took a while to figure out, but basically, these gamma ray bursts come from very far, they come from outside the galaxy. So here what we see is a histogram, and don't worry about the inset, but yeah, here is a histogram of redshifts measured for gamma ray bursts. So in the light gray, you have long gamma ray bursts, where the average redshift is about 2. In the dark gray, you have short gamma ray bursts. And I highlighted a couple of different redshifts and exactly what it means there. So a redshift of 1 means it's about 3 gigaparsecs away, and we just talked about what a parsec is, 10 to 25 meters. So it's a number you can look up on Google. And then this happened. That means also, if it's 3 gigaparsecs away, with some assumptions, it basically happened about 6 billion years after the Big Bang. If you go to a redshift of 4, that's 7 gigaparsecs away, and it happened only 1.5 billion years after the Big Bang. If you go up to a redshift of 9.5, which is the farthest we've ever measured a gamma ray burst, that occurred about 500 million years after the Big Bang. So when you study GRBs and you study gamma ray bursts, you start to see the really far away ones, and that starts to give you some ideas about maybe what happened, what was going on soon after the universe began. Oh yeah, I wrote, okay, yeah, gigaparsec is, okay, yep, 3 times 10, 25 meters. There we go. So a gamma ray burst, in general, what do we see? We see this bright flash of gamma rays, and then we see this long-lived fading emission. So that should be pretty straightforward. But what you're seeing on the right here, for instance, is you're seeing a couple of different afterglow light curves. So this is in X-rays, and this is just how the emission fades in X-rays over time. And you can see that one of them, the black one, the black set of curves, is sort of, just kind of flat, and then it drops down, and then it's very well behaved, right? Everything is very smooth. You look at the red curve, and you realize, wait, okay, so it drops down a little bit, and then all of a sudden it rises up again, and then it comes back down. And then with the blue curve, it just sort of always steadily fades down. And so you start to realize that not only is the prompt emission really different, so the bright flash of gamma rays, that's the prompt emission, not only is that really different, but the afterglow emission is also often very different. So if we just do a couple of calculations here, basically, if you look at a GRB, you take a GRB, you take how much energy has been emitted, and you say, okay, it's emitted something like 10 to the 54 ergs in less than a minute, let's say. And then if you look at that, then you notice that 10 to the 54 ergs, that's approximately, I think that's about the rest mass, the rest energy of the sun. So if you do MC squared for the sun, that's about 10 to the 54 ergs. It's also the amount of energy that's emitted electromagnetically, so in photons, in a supernova. And so you make these connections and you say, hand-wavingly, that at least some GRBs are linked to the core collapses of massive stars. So at least some GRBs, ones that are this energetic, must be linked to massive stars collapsing, are probably linked to supernovae. So there are 2 types of GRBs. What we have, so another thing is astronomy. Terms are basically determined historically, right? We notice that some GRBs are really short and some are really long, so we call them short and long GRBs. The duration, so where you split that's around 2 seconds, but that's not perfect, right? That's not perfect because a lot of these detectors, let's say your background level is over here. If your background level is over here, I don't have enough hands. Hold on. Did I turn this off? No, we're good. All right, your background level is up here. Let's say your bright peak is up here, right? Your bright peak is over here. It's this tall. Your background level is over here. You might, it's like this. Whatever. One duration for that. If your background is much higher, you might measure a shorter duration. If your background is much lower, a longer duration. So that's not quite perfect. It's also difficult because this measurement of duration also depends on what energy your instrument is sensitive to. If your instrument is sensitive to very low energies, you might measure something different than if your instrument is sensitive to very high energies. But roughly speaking, GRBs, short versus long, they're split at 2 seconds. But as you can see, there's sort of a gray area in between when it could be either short or long. And there's also the problem of, if things are really far away, they're redshifted, right? And everything gets all the time expanded a little bit, right? Time is also redshifted, and therefore the duration also, if something's really far away, might be longer than it would be in its own rest frame. So in general, this is sort of like an overview of GRBs. GRBs either come from two compact objects merging. I guess I haven't really told you about why that's so. We'll talk a little bit later about that. Two compact objects merging, or one very massive star collapsing. In either case, you either have a black hole with an accretion disk around it, or you have a very heavy neutron star, or a magnetar, so very heavy, very highly magnetized neutron star. So in either case, it's unclear which one of these you have. But in both cases, you have something in the middle that's launching a jet. There are interactions within the jet. So when you launch a jet, everything's very energetic. You launch a jet. When you first start out, basically, the photon produced within the jet cannot escape. So it takes a while for the jet has to keep propagating and slowing down, and everything has to cool a little bit. At some point, photons can escape. That's when you get the prompt emission. And then later, the jet kind of hangs out, and then it hits whatever material is surrounding the star that was left there before, or from the interstellar medium, let's say, and then it plows the material to the afterglow, the sort of long-lived fading emission. So roughly speaking, this is what a GRB is. That's it. So, but how do we know? All right, so I kind of hand-wavingly said, well, long GRBs relate to core collapses of massive stars. How do we know this? This was relatively straightforward, because what happened was let's see, I think this was the first, I'm not sure, no, this might not be this is one of the first GRBs, but this is a bright one. So what happens a lot of times is we detect a long GRB, and it's very bright, and then, the instruments detect it, and they say it's at that part of the sky, and so then you point your optical telescope to it, and then you look at it, and you say, oh, that looks like a supernova. Because each one of these astronomical events has a very different spectrum. What that means is that some of them emit all of their energy at the some of them emit all their energy at wavelength, some of them emit their energy across, a wide range of wavelengths. And so every different kind of event has a different spectrum or a different fingerprint. And so when they looked at this more closely, when they looked at GRBs more closely, they realized that a lot of long GRBs came with core collapse supernovae. The other thing is long GRBs are often found in sort of the brightest, most active parts of the host galaxies. What you're seeing here is a bunch of pictures in optical, and I don't remember probably Hubble. I don't know which telescope this is, but if you look at it, and it's kind of hard to see on here, I know. So sort of red and yellow, this is the optical data. And you can see a lot of these, you can see either a galaxy or multiple galaxies, and there's a green cross in the middle of these, or that shows what GRB is. Anyone want to speculate why long GRBs are often found in the brightest and most active host galaxies? So we know that long GRBs come with supernovae, core collapse supernovae. No worries. Long GRBs come with core collapse supernovae. I guess that was just the answer. Looking for anything profound. That was it. And that's, if you have core collapse, if you have a lot of supernovae going on in one area, that's just going to get brighter. If you have a lot of supernovae, you really have these more massive stars. Massive stars produce more light. And so, yeah, that's it. That was the answer. I'm sorry, that wasn't very profound. Realized. Ooh, here I have a video. So what happens, we have a long GRB, right? All right, we're zooming in. Here is the envelope of a very massive star. And inside, the core has collapsed, and it produces a jet, and the jet punctures through the envelope. And we see the jet keep going. And at some point, within the jet, we get the prompt emission, and then I didn't rehearse this. All right, it's taking a while. Yes, so now you see that the jet's starting to hit the material outside, and because it's hitting that material, it's starting to spread out a little bit, and then it's heating up the surrounding medium. And if the jet just happens to be pointed at us, because these are jetted events, they're not isotropic, if it's pointed at us, we see a bright flash of gamma rays. Oh, that was fun. So yeah, so this is actually, yeah, so this is data from the Fermi data lab from one of the, I'll talk a little bit more about Fermi later. Short years. That from the mergers of objects. Why did we think for binary mergers? We had never detected a binary merger recently. So until last year, this is all sort of kind of not conjecture. It was all sort of, we would say short years are consistent caused by the mergers of two compact objects. One thing that people did was, I mean, they looked for supernovae, short GRBs as well. Short GRBs also come with supernovae. So what you're seeing here, the plot, on the vertical axis is, let's see, magnitude. It's basically optical brightness. So magnitude is also something that is a term. So what we have is the optical brightness, and then on the x-axis, that's redshift. What you're seeing is, let's see, the red points at the very top. These are the brightnesses of supernovae that are long GRBs. And then the histogram on the side, the gray histogram, that right, sort of just regular supernovae are, that are this type of supernovae are. And then these arrows, all these triangles with arrows, these are upper limits, right? So an upper limit, I mean, best case scenario, detection, right? If you don't get a detection, you can still calculate an upper limit. So the idea is, if I have a detector somewhere and I don't see anything, but I know how sensitive my detector is and how much I detect, then that gives me an upper limit on how much stuff actually was there. What happened was when they searched for these sort of supernovae associated with short GRBs, they couldn't find anything, and they went to even farther. They went to very deep magnitudes, and they still couldn't find anything. Yeah, magnitudes are also weird because higher numbers are actually dimmer, and lower numbers are brighter and also. So magnitudes are kind of weird. Is anyone here an optical astronomer? All right, good. I can badmouth magnitudes. That's fine. The other thing. So we talked about how long GRBs often come in the brightest active parts of their galaxies. Short GRBs, when they looked, they were really far from the centers, they're far from the brightest parts of the host galaxies, and a lot of times for short GRBs, it's very hard to figure out what host galaxy it actually came from. Anyone want to speculate as to why this is? If we already know, for instance, that short GRBs come from the mergers of compact objects, the why then coming from sort of far away from galaxies. No worries. So all right. So one reason we thought they might have come from the merger of compact objects. And I'll talk a little bit more about this later. I'm realizing things are a little bit out of order here. So you get a neutron star or a black hole. You get a neutron star or a black hole for the most part when you have a fairly massive star. So definitely like about 5 times, 10 times more massive than the sun. When you have a massive star and it dies. When it dies, it's behind a neutron star or a black hole. And so that generates a lot of energy, right? So you have the core collapsing, and then if it's heavy enough, then everything will collapse right into material, and that releases a lot of energy at once, and so everything else is shot out. If it's not heavy enough, the core collapses as a neutron star, right? As a neutron star, all of a sudden you have this very dense material in the middle there that you can't, and so everything kind of bounces off of that, right? It bounces off of that, and then it shoots out into space. If you have your supernova, if anything is slightly asymmetric, if everything's completely symmetric, that neutron star is just going to hang out where it is. If anything is slightly asymmetric, that neutron star is going to get a kick in one direction. And a supernova deposits a lot of energy. It's going to get a very large kick in a direction. And so what happens a lot of times is a binary merger, let's say you have 2 neutron stars, both of them had kicks. And so the whole system has been shot out, has been shot out of the galaxy, or has had a very large kick at birth, and then it keeps on evolving and just keeps on going farther and farther away from the galaxy. So this was sort of circumstantial evidence where we said, all right, they're consistent with being caused by, let's say, 2 neutron stars at a black hole, or even things that are more exotic than that. There was also, so this is GRB, yeah. Yeah, so okay, so the question, yeah, can GRBs be used to estimate the age of the galaxy? So are you talking about the core collapses or the binary mergers? Yeah, so the difficulty about the binary mergers, right? So the idea is, if I'm getting it correct, is that you kind of, yeah, if you work sort of backwards in time, can you figure out approximately how old that galaxy is in order to produce a binary merger over here, for instance? Is that right? Mm-hmm. Yeah, I think, yeah, I might still be. I apologize if I'm not, if I don't answer the question correctly, or what you're asking. I think part of the problem is, so the question is basically, yeah, can you go from the GRB observation and then work backwards to try to figure out the, is that right, or am I misinterpreting your question? I'm still misinterpreting your question, aren't I? Yep. Okay. So if you can, yeah. Hmm? Okay. So the question is, yeah, if you can, okay, so if you can associate the events with with young stars. The problem is, I don't know if you can, right? So I mean, so long GRBs you kind of associate with very heavy stars. Short GRBs you actually associate with much older stars because the star has to have had time to go supernova first. Not only that, both stars had to have time to go supernova and to get out of their galaxy. So it's very difficult, I think, to work backwards from the GRB, from observing a GRB to try to figure out the host galaxy's age, because stars are going supernova in a galaxy all the time, right? So you need to, so there's that. And then how long it takes for a star to go supernova and for a star to explode, and how long does it take for the two objects to merge? There's a lot of variation, and this is very dependent on things like the mass of the star and the contents of the star, how much heavier elements are in the star and things like that. So it's a little bit tricky to do for individuals, but it might be possible to do it sort of on a collective scale by looking at all GRBs, for instance, yeah, that are really close to us, that I'm not sure about. So yeah, so you guys already know about kilonova and how it exists and how roughly speaking, you have, let's say, a neutron star, or a neutron star black hole, or things that are slightly more exotic. I'm just going to keep with the very non-exotic objects here. So black holes or neutron stars. So a while ago we said that, all right, short GRBs come from two objects merging, maybe two neutron stars merging. In case, if you have two neutron stars merging, you should get a kilonova. That was predicted before they were observed, predicted a while ago. And so people were really looking for these kilonovae for examples of this. It's very hard, however, to detect one. Yeah, I mean, as you guys are more experts on this than I am, because you were here for the math of this and I wasn't. It's very hard to detect one, right? Daniel, why is it hard to detect a kilonova? That's why. You were all here for it. Yep. Yeah, okay, yeah, super dim, spread out over long time scales, very hard to detect. What do you have to do, practically speaking, what do you have to do to detect a kilonova? You have to tell, a very powerful instrument, very powerful, like Hubble or JWST in the future, you have to tell them, hey, point your telescope over there, I think a kilonova might be over there, look and see if you can see any. And practically, it's very hard to get time on Hubble because everyone wants time on Hubble. Everyone wants Hubble to look at their thing because there's only one Hubble out there. And so practically speaking, it's hard to do. It's hard to convince people to look at it. And then physically, it's just very dim. It's very dim, and so it's hard to find. And so what people, were chasing after these kilonovae, there was the first hint in 2013. So this is one GRB where, here we go, on the right, what you're seeing now is the light curves for 3 different energy ranges, let's say. So the black is the X-ray light curve, and that just fades. The blue is optical at sort of bluer or higher energies, or shorter wavelengths. And then the red is optical at lower wavelengths, maybe infrared, I'm not sure exactly, probably infrared. And so what you're seeing here, blue and the black fade together pretty well. And you would expect the red to fade together with it. You would expect them, the spectrum to be all well behaved, because basically at this point, the jet is just plowing through material and nothing weird or crazy is going on. There's no new energy injection. So if you expect them all to fade in the same way, you would expect the red to fade slowly like that. But what they saw instead was an excess in the red. So that's the first hint of a kilonova, was this one little bump up here, one data point. It said the red should have been going with the line, and instead it was up here. And here, movie. So, oh, this one comes with sound. Nope, let's turn it off. This sounds really silly. Wait, that's the wrong button. Oh no, you're getting the sound. All right. You're getting the music with it now. Ooh. All right, that was dramatic. So what you get in the beginning, you get 2, let's say, neutron stars. I'm just going to say neutron stars. Luis isn't here. You get 2 neutron stars. They're slowly spiraling into each other. They're emitting gravitational waves. They spiral faster and faster. They merge. When they merge, they produce these jets. And then you see there's a slower, this is what we predict maybe the kilonova producing emission would have come from. And then here you have the jet. This is the Gammarays. And then, okay, that's it. Yeah, I guess that was all. All right, so now we know what GRBs are. We know where they come from. I don't remember what I have next. Yes. All right, how do we know? So I've been talking, how do we know the emission? I mean, the sun gives off a lot of emission, and that's isotropic, right? That's directions. How do we know GRB emission is not isotropic? How do we know that it's in a jet? Basically, what happens is, how we know is by looking at the afterglow, the X-ray afterglow. So what you're seeing here on the left, here are 4 different X-ray afterglows that are sort of kind of standard. So this is data from, so this is X-ray data. This is data from the Swift X-ray telescope, XRT. And what you're seeing, and then the different colors, blue and red, these are just different data taking modes. So what you're seeing is that a lot of them, they sort of fade, and then it's just sort of a broken power law, right? They fade, sometimes they fade rapidly, sometimes they fade more slowly. But in general, what you have is just a set of power laws that kind of change slope once in a while, right? So they're fading at different rates at different times. On the right here, what you're seeing is sort of a theoretical, quote unquote, canonical afterglow. This is kind of a 0th order explanation or sort of understanding of what afterglows in general look like. In this case, I'm going to say very much from a data analyst observer perspective. So I'm not going to talk about sort of the emission mechanisms and things like that. Daniel will talk about the math. So we have the canonical afterglow. What are the different parts of it? Oh, great. That's not actually afterglow. It's the prompt emission. So the prompt emission, and I know it's flat up here, but obviously, like we saw, it could be very peaky. So you have a lot of peaks in gamma rays. That's fine. That's caused by things caused by interactions within the jet. Interactions could, what was I going to say? Yes, those interactions. So one idea of what those is, you have sort of these shocks that are released, or these shells that are released by the jet. Let's say, or sorry, released by the central engine. So let's say it emits something, right? So it emits something, and then it emits something that's a little bit faster. When the faster one catches up to the slow one, it shocks it, and all of a sudden you get a lot of compression of magnetic field, compression of densities and pressures, right? And so from here, you get a lot of energy deposited at once, and a lot of particles accelerated at once. Oh, I think I can't walk past there, sorry. You get a lot of energy deposited into the particles at once. Those particles have to do something. They have to cool, they radiate. And then they radiate these gamma rays. And so from those, because you have these shocks and these sort of very explosive kind of powerful events, that's how you get these peaks. Because one thing you have to explain is, why do you get these spiky peaks? There's also other potential ideas involve magnetic fields. That part I'm not very good about. I'm not Yeah, but basically, you expect it to have strong magnetic fields. Daniel?
No.
Okay. All right. Anyway, so another idea is, another idea is basically you could have accelerated along the magnetic field lines, and in the jet, you're expected, again, you have sort of compressed magnetic fields, and if you have the particles accelerate really fast and stuff, then again, you have. That wasn't a very good explanation. Do you know magnetic reconnection? I don't know magnetic reconnection.
Wait, sorry, so you're talking about the afterglow, right? And the magnetic field producing the afterglow?
Prompt emission.
Prompt emission, sorry.
Yeah.
I'm not talking too much about the dissipation mechanism.
Okay.
But
Okay.
yeah, I mean, there's magnetic field reconnection and these kind of things that can dissipate the prompt emission and the gamma rays.
Okay, yeah. So the main thing is that you need something that's accelerating particles, and that could come from the magnetic field processes, or it could come from particle-particle interaction, like that, or photon-particle-photon interactions. Anyway, the central engine is active, and things are happening along with the jet. Things are happening inside the jet. And then the central engine deactivates, let's say, and so everything inside the jet is kind of floating along. And so when that happens, then when things are no longer active, the emission decays, and it decays pretty rapidly because there's nothing powering it anymore. So that's fine, except that at some point, instead of decaying very rapidly, it smooths out again, and it stabilizes again. And this doesn't happen in all GRBs, but it happens in a set of GRBs. And the explanation is maybe there's some long-lived central engine activity. It's not clear what the answer is, but so this is one of the mysteries, I think, about GRBs, is what causes the sort of slowdown of the decay. After that, at some point, the jet is going to interact with the surrounding material. It's going to decay in a different way. This is well predicted and well behaved, and this is well sort of modeled and everything, and then it sort of has this kind of slope down here, and then at some point, it decays much faster. So called a jet break, and then this little point over here is decaying all of a sudden much faster. That is the jet break. So that's the very last point over there. And now, what do I mean by jet break? So we have the jet. So we have relativistic jet where the bulk Lorentz factor is greater than bulk Lorentz factor. So probably had a special relativity class, right? Where you talked about just how fast is related or compared to the speed. You have things that are really relativistic. Capital gamma bulk Lorentz factor just means what is the overall speed or the overall Lorentz factor of the jet, because everything within the jet is sort of moving all over the place, but the entire bulk motion. That's all the bulk Lorentz factor is. So you have a jet. Because it's relativistic, everything within the jet is going to be relativistically beamed. So what I'm showing on the right is a little GIF of something that in its own reference frame is isotropic. But because it's moving really fast in that direction, everything is everything is beamed, everything is boosted in that forward direction. And so it looks like everything around it is sort of coming from a very much smaller angle. It's isotropic to an observer that's over there. So if that's what happens to something that's isotropic, that happens even more strongly, or not. It also happens if something is jetted. If you have a jet that's moving relativistically, that also experiences relativistic. And so what happens is that, in that case, let's say you're looking right down the center of the jet, only a certain part of it is going to be beamed at you, right? So initially, sort of at this wide angle, but now if it's fast that way, then everything is going to be sort of beamed along this angle, right? And so it's a much smaller angle. And that means if you work backwards, then the observer is seeing a portion of the jet at once. It's only seeing a small portion of the jet at once. And so the brightness that you observe is just a combination of the flux density multiplied by the viewing area, right? Because you're not seeing the whole jet, you're only seeing a portion of the jet. Now, as the jet propagates, it slows. So as it slows, and it's not beamed as much, and so everything is kind of widening out. And so if everything is widening out, so before the observer was only seeing this much of the jet, now it's seeing kind of this much, and so when it works backwards, you actually see, let's say, the whole jet. And so when that happens, your flux density is still dropping, your viewable area is sort of increasing at this point, and your observed brightness is starting to go down a little bit. And then at some point, you see the entire jet. At some point when you see the entire jet, and it's still slowing down, when you see the entire jet, then your viewable area is no longer increasing, the flux density is dropping, therefore your observed brightness drops, right? And so that's how you get a jet break, is that all of a sudden you're not seeing any more of the jet, and it's still dimming, and so all of a sudden then you get this break. Here, what is a visualization of sort of what we were just talking about, what I was just talking about. On the left, what you see, it's kind of hard to see, a yellow circle, a yellow kind of large, and that's just the jet. In the gray circle, that's the viewing angle of the observer. And so this is assuming we are looking at the jet right down the middle. So that's the viewing angle, and what you're going to see is yellow, big yellow circle, it's going to get darker and darker. It means the jet is losing energy, or the bulk Lorentz factor is dropping. On the right-hand side, what you're going to see is the flux and over time. So you're just going to see a light curve. So what happens? As the jet is slowing down, jet is slowing down, and then the viewing angle is increasing, and then, so this is actually maybe not the best descriptor. Okay, so there's a jet break. You see there's a break in the light curve at around 10 days. The one at 100 days is a sort of I think is a plotting artifact, so don't worry about that. But there's the slope change steeper at around 10 days. If we look at this again, can I stop it? Oop, nope. Right. All right. Anyway. Yep. So basically, what's happening is the jet is slowing down, but at the same time, your viewing angles, how much of the jet you can view is increasing to compensate, and then at some point you no longer see any more material, and so it just drops all of a sudden. What happens? Use that jet break to say that. And then you use that jet break and you work backwards and you say, all right, what size of the jet that must have caused a break to happen at, let's say, 10 to the 4 seconds right there. In general, later jet breaks mean wider jets, although this is a little bit more complicated than that because there's questions about how fast the jet moving, because at some point the jet is also, when it hits the interstellar medium, at some point it's also going to and it's not going to be jetted anymore. And then, depending on the density of the surrounding environment, if the surrounding environment is very dense, it's going to, the jet is fast. If the surrounding environment is not very dense, the jet is going to plow. This is another difficulty in GRB observations and trying to analyze GRBs, because there's differences not only in the progenitors, so are they binary neutron stars or a very heavy core collapse of a very massive star. So there's that difference. How each of the light curves, we saw how the X-ray light curves were often. Also, the surrounding environment is different. And so these are all to disentangle in GRB analysis. Based on that, people were able to kind of constrain the opening angles or how wide GRB jets are. What you're seeing here is a histogram of the opening angle of GRB jets from this type of measurement. In red are the long GRBs, and blue are the short GRBs. You'll see a lot of these little histogram, little squares have triangles. That just means this is either a lower limit or an upper limit. It means we don't know exactly how wide it is, but it's at least this much or at most that much. GRBs, let's see, long GRBs can be as wide as 35 degrees. Short GRBs in general seem to be a little bit narrower, but it's hard to say exactly because we don't have any measurements of opening angles. All right, so okay. Or the afterglow just comes from things interact. Yeah. Yep, go ahead.
You're always assuming that the jet is coming directly to you.
Yeah. In this case, especially what I'm talking about, we're always assuming that we're looking just face on, just right down the jet of the GRB. Yeah. That's an assumption we've always made, just because that's sort of, if you don't know going on, you have to make some assumptions. You have to start with the simplest case, right? So we always assume that. And, but yeah, as we've seen recently, right, with GRB and everything, that's not necessarily always true. So it could be that maybe we go back to these GRBs and try to figure out, is it maybe what happens to these models, what happens to these histograms, let's say, if we assume slightly different angle. So yes, and everything I'm talking about, I'm just assuming on axis for now. So we saw how the afterglow decreases, or the afterglow flux decreases And most of it's very well predictable, but sometimes thousands of seconds central engine, after the prompt emission has shut off, you still get a flare, an X-ray flare. And this is one of the sort of GRBs. You have something very explosive that happens, something very explosive, a lot of energy shoots out at once, that's great. Thousands of seconds later, all of a sudden you have another explosive event. What's going on there, right? Because if you have a massive star that collapses into a black hole, and the black hole has an accretion disk around it being fed by the accretion disk, how long can you actually support that accretion disk? I had Rodrigo last week, right? And he told you, so you are all are experts on accretion right now, right? I don't know much about accretion disks, but basically it's very hard to sustain them for a long time, right? And so how to explain not only for seconds or thousands of seconds, but all of a sudden there's a new injection of energy that's almost as powerful as the original injection that came from the first explosive event in the first place. Question mark. So signs in there's something going on in the central engine much later than the after the prompt emission ends. So this is another one of the mysteries of GRBs, is what could cause, let's say, these flares or these plateaus in the afterglow emission. What's causing things to not fade like you would expect them to just fade? Another example of this type of confusing, sort of not obvious behavior, here is an example of a GRB that lasts for 1,000 seconds. So that's already pretty long. Right? Somehow, whatever's happening is sustaining it for 1,000 seconds. I mean, still, at least it's long. So that's a little bit in its own rest frame. So it's difficult to explain. The other thing is, let's say you have something that's going on for 1,000 seconds. Was I talking really loud? I think I talk really loud. It's fine. If you have something going on for 1,000 seconds and you have this first emission episode at 0, so you have this first bright flash at 0, and then nothing. Nothing for hundreds of seconds. Something is happening there. You have the first explosion of energy, and all of a sudden it just goes back to nothing, to stillness before it rises again. So what's going on there? We see this in about, let's say, 10 to 20%, where there's a very long, what we call quiescent period in between, and that's hard to explain as well by some of these models. Sometimes, as we see here, the first peak is a lot dimmer, and that's also not clear why. Right? If something is exploding, naively you would expect the very first emission episode to be the strongest one, because that's when basically you would naively expect the first emission episode to be stronger and then later ones be weaker, and that's not what we see. So let's see. Yep, it's a reminder that this is what we're talking about. Talk about GRBs, and back to the question of the central engine. What is central engine? What is launching the GRB jet and what's causing all this emission? So for a while, the main theory, and in some ways the the more natural model, is you have a black hole with an accretion disk. In a sense, this is natural. It's really easy to launch jets in this case. There's some relatively easy to launch jets. We've done mathematically, we know how it works. Simulations have shown you can get the jet from black accretions. I mean, we know active galactic nuclei. I think Rodrigo talked about this. We know that supermassive black holes can accrete material and launch jets. So stellar mass black holes that are this size, roughly tens of solar masses, should also be able to launch jets. That's fine. But the problem is, like I was saying, sometimes we see some kind of new energy injection thousands of seconds later. And that's very hard to explain with an accretion disk, because you would expect this to happen, and you expect material to fall in, and then what do you have left? There's nothing you have left. It's gone. On the other hand, you could have something that survives for a long time, like a magnetar. So a magnetar is just a neutron star whose magnetic field is so strong that any kind of behavior is basically dominated by the magnetic fields, or is the magnetic fields. So you have a magnetar. It's a millisecond magnetar. That just means it's spinning really fast. The spinning rate is milliseconds, roughly. So millisecond magnetar, that can survive for a while. That can survive for thousands of seconds. That's fine. And then you could sort of explain a much wider range of these temporal behaviors. but it's really difficult to launch a jet from millisecond magnetars. I think we haven't got simulations yet, so this is sort of a problem where theoretically this could explain some of this long-lived temporal behavior, but how do we get a jet in the first place from this? So one of these things I was talking about, this sort of plateaus in the X-ray afterglow, that's one of the questions. This sort of subdominant emission. Just a reminder, we know after the prompt emission fades, all of a sudden the X-ray afterglow starts and all of a sudden it drops really quickly, it's fading. And then all of a sudden there's a plateau. What's causing that plateau? Probably some kind of underlying emission mechanism. What's that underlying emission mechanism? That's just jargon to say there's something there that we don't know. But so what I'm showing here is a paper where you're looking at the X-ray light curves, and here they have this model where what's causing that plateau is actually a millisecond magnetar that's sort of long-lived and it's hanging out. And then at some point, that millisecond magnetar, it's really heavy, and so then that collapses to a black hole. All of a sudden, you have nothing left, and then you get a sharp drop, or a less sharp drop, depending on the model. And then the other thing I was talking about, these quiescent periods. What happens if you have a sharp peak, or you have a lot of energy injected at 0, nothing for 60 seconds, and all of a sudden another peak? Also very difficult to explain. How do you switch the engine off or on and then on again? So some of these models, they look at, let's say, pulsars. So pulsars, neutron star with a radio beam, right? So it's emitting radio emission, let's say. And depending on the sort of, depending on how the magnetic field is and how fast it's rotating and how fast the magnetic fields are rotating as well, you can actually switch a pulsar on and off. And so some people are starting to look at, well, can we apply that to, I mean, they're both neutron stars with strong magnetic fields. Can we apply this to GRB central engines and use this to explain why this is switching on and off? All right, so we talked about there are two types of GRBs. What's relevant here in this workshop is short GRBs, right? Short GRBs we've detected also having gravitational waves coming from this event. In general, GRB is different from long GRBs. In general, short GRBs release less total energy than long GRBs. This can be kind of understood because in the amount of energy that's available from two neutron stars merging, and when I say energy, I mean electromagnetically. So two neutron stars merging, two neutron stars, a massive star collapsing. So the masses are going to be different in that case, and sort of mechanisms are different in that case. Short GRBs have harder spectra. What do I mean by that? So when you talk about, so there are different ways to talk about emissions. We learned a little bit about thermal emission. Basically, whenever you have thermal emission, this is zeroth order understanding. Whenever you have thermal emission, you sort of have this black body peak, let's say. When you have non-thermal emission, what is non-thermal emission? Non-thermal emission is when it just doesn't look like this. It's not, it's not peaked like this, and you can't temperature. Non-thermal emission comes from charged particles that are accelerated and that then decelerate or then radiate energy and slow down. So whenever you have non-thermal emission, that means you have charged particles accelerating within the jet, let's say. So charged particles accelerating, the spectrum no longer looks like this black body peak. The spectrum looks kind of like a wider, sort of smoothly broken power law, right? Depending on who you ask, depending on the mechanism, it might look a little bit different, or it might look a little thinner or wider, but it's no longer just a black body peak. The smoothly broken power law. And if you have, when we talk about things like, so when we talk about black body spectra, or we talk about thermal emission, we can say things are hotter or colder or cooler, right? Because the only thing that determines the shape of the spectrum is just the temperature, right? So something is, it goes like this, if something's hotter, it goes like that. That's fine. Non-thermal spectra, what you need is you need a power law, lower energy power law, alpha, let's say, a beta, and you need an E peak or an E break or something like that. I'm going to say E break. I don't know why I'm right. It doesn't matter. So with a thermal spectrum, you don't say things are hot or cold anymore because that doesn't have meaning anymore. What you say is that things are harder or softer. Harder just means that there's more energy emitted more of the total energy is emitted at higher frequencies or higher energies. Softer just means that there's more energy emitted at lower frequencies, lower energies. It's basically the equivalent for hotter and cooler in non-thermal spectra. Short GRBs are also harder to get redshifts for. Anyone want to speculate why this might be true? So in order to get something, I guess I haven't talked about how to get a redshift, but in order to get a redshift, right, you have to know exactly where something is, and you have to be able to take a really good spectrum of it. Why might it be hard for short GRBs, harder than for long? Right, if we talked about, I mean, they're short GRBs, so that's already kind of a problem. They lack total energy than long GRBs. If they release less energy, in total, overall, they're going to be a little bit... No, that's not a good explanation. All right, never mind. Yeah. All right, now this was a couple of steps in logic. So short GRBs, we had said a while ago that they come from mergers, and they come from parts they far away from the center of the host galaxy, right? Remember that plot we showed with we had with a lot of host galaxies, and the short GRBs were kind of far away from the bright parts of the galaxy. Far away from the bright parts of the galaxy, that means they're in regions that are not very dense. If they're in regions that are not very dense, that means there's not a lot of material, there's not a lot of burst material for them to plow into for the afterglow. If there's not a lot of material for them to plow into, then that means there's not a lot of particles to get accelerated, not a lot of particles get accelerated, not a lot of particles radiate. That's all we're seeing. We see afterglow is particles accelerating and then radiating. If the particles aren't there, then we're not going to see the afterglow. And so what happens is for short GRBs, you don't get a lot of afterglow detections. And again, part of the problem is entangling how much of that is intrinsically because GRBs are somehow different, or because observationally they're different parts of the. Let's see. Yeah, and in general, GRBs are observed to be closer to us in general than long GRBs. Just because they release less total energy, they're just a little bit, on average, sort of or energetic. If they're less energetic, then we just can't observe. They have to be relatively close to us to be observed. So let's see. There was a previous GRB, a previous short GRB that we thought we might have seen a kilonova for. I guess I don't necessarily want to talk about this. Yes, I could. Yeah, this is redshifts. How do we get redshifts? All right, what we're seeing on the left is a spectrum of the short GRB, and sometimes, so for GRB, sometimes we take the spectrum of the afterglow by itself, sometimes the spectrum of the host galaxy. So we see a spectrum over here, and what you'll notice is, all right, so this is just how much energy is emitted over different wavelengths. So what you notice is that there's sort of this smooth behavior, but then there's some lines here, right? There's some areas where it's sort of where there's not as much emission expect just from the smooth underlying spectrum. What that is heavy elements, right? So that's heavy elements by heavy. All right, so in astronomy, anything that's heavier than helium is a heavy element. Anything that's heavier is a metal. So when we talk about metals in astronomy, it's heavier than helium. So what happens is you have, let's say, a lot of photons, a lot of emissions, and then you have calcium hanging out over here in the way. So the photons get to the calcium element, and then they get absorbed, right? Because calcium has these energy levels, and so at particular frequencies or particular wavelengths, preferentially absorb that photon, right? So absorb that photon. When you have thousands, millions, billions, a lot of calcium atoms, let's say, calcium nuclei, you're going to start getting a lot of these. Yeah, you're going to start to pick up you're starting to get a lack of emission at that frequency or at that wavelength because it's all been absorbed by the calcium. On the right, what we have is the spectrum let's see. Yeah, this is the spectrum of the sun. So this is something that's really close to us. See what I've shown here. So you can see these two at around 300 nanometers. You have these two lines for magnesium, and then 400 you have calcium, and then over there at 700 you have, helium alpha, H alpha, sodium iodide, things like that. You have basically spectral lines from a bunch of different elements or molecules, compounds. On the left, what happens is those lines have gotten shifted. So let's look at calcium, the calcium lines. In the lab, the calcium line, let's see, yeah, the magnesium lines in the lab or at the sun, they show up at around 300 nanometers. From this GRB, the magnesium lines show up at 400 nanometers. This is simply a calculation of, this just gives you the redshift automatically. All you do is you take the difference in your wavelength, so 400 minus 300, we get 100. Divide that by the wavelength in the, is that right? By the wavelength in, I believe it's that wavelength, the redshifted wavelength. So that's 300. Nope, it's that wavelength, 300. Yep. So what we have is 100 divided by 300, 0.3. And the actual, or estimate of 0.3. The actual spectrum, when they really looked at it closely, was redshift 0.36. So just doing this rough estimate, we got pretty close. So this is all we're doing when we're calculating redshifts and we're determining redshifts, is we're taking a look at the spectrum and we're trying to see where are there lines, emission or absorption lines in the spectrum, comparing that to what we expect in the lab or nearby, and we're saying that these must have been redshifted. We are this until August 2017. This is what we knew about short GRBs. We knew they probably come from emerging compact objects. We knew that they might come from kilonova emission or come with kilonova emission. And that sort of sets the scene for, I guess I'm going to be talking either next hour or next afternoon. So I think that's all I prepared for GRBs, but I have a little bit extra we can talk about if you guys want. Any questions right now, actually? All right, questions. How do we actually GRBs, right? What's practical, right? Because I'm an observer. What happens when a GRB goes off somewhere? Practically speaking, what do? How does everyone communicate, right? Because as we've seen, it's important to tell, let's say, the optical observers to go look for a kilonova or a supernova. It's important to tell the radio observers over there for long-lived radio. So how do we communicate all of that? And how do we know how to tell them where to look? What happens? Let's see. You have, let's say, an instrument like Fermi or Swift. These are gamma ray detectors. These see a lot of the sky at once. GRB comes in. So things are. So what's important is to be able to get the localization out to tell the instrument where in the sky it is really rapidly. Instruments like Fermi and Swift, these high energy detectors, a lot of times they will have sort of onboard real-time automatic GRB localization algorithms on the spacecraft. That's a little bit tricky because you can't put a lot of stuff on a spacecraft and you don't have a lot of computing power on a spacecraft. And so what a lot of times what will happen is you'll get a localization that gives you a very large part of the sky. Then it gets tricky again because, excuse me, you have a localization that's a really large part of the sky. And then you have to wait for the data to come onto the ground. Then you sort of have a much better localization with your computers and things like that. And then you have to extra observers where to point. So there's a whole set of, so for Fermi and Swift, there's someone on duty. There's always someone we call, I guess, first advocate, someone on duty to keep tabs, communicate with the energy, with the other spacecrafts, sort of, or the other telescopes to sort of do observations. There's a whole set of communicate. About years ago, I think 20 years ago, started circular networks, or GPNs. Everyone has, their own like that, and you're curious and you want to go follow up in these bright events, you can just look up GCN circulars, GCNs, and actually follow along to the story in real time of someone say, there's a gamma ray burst over there. Someone else will say, oh, that's exciting because LIGO detected something right around that time, and then everyone will look in that direction. But it happens, so for 99% of GRBs, they're kind of, they're not maybe the most exciting. GRBs are sort of standard, so a lot of the time it's just a matter of, let's say, what are the most exciting ones? Things that are bright, things that are really high energy, things that are really, really close, things that we can get a redshift for, things. Are there any questions right now? Anyone want to talk about? I think that was unclear before. Yeah.
Can you more about this short jargon that you mentioned that
Yeah.
follow up?
Unfortunately, I'm not an expert in this. I will tell you a little bit of sort of GRB field gossip. So this is a little bit, right, a lot of people wanted to detect the kilonova, and like I said, it's kind of hard to get scope time at these really fancy or really sensitive detectors to get the kilonova, your source that you want them to look at. One group in, I think, in the UK, they're the ones who had this sort of, they had this Hubble, was it Hubble? Probably. Look at the group and actually are the ones who got the data, who asked for the data, got the data in the first place. The problem is, at some point, that data becomes public, and so another group decided they were going to swoop in, take, and publish it ahead of time for the first group. So that was kind of an interesting time. This is what happens, I think, when you do transient astronomy, is that because things happen so fast, you have to really get on top of things, and then, a little bit sharky, let's say. Close. It's just bright, short, energetic, close. And so that's why they looked at it. And what you're seeing on the left here are, so these are the optical images, or I guess infrared. So at the so these are just two different wavelengths. The top row is a shorter wavelength, so slightly higher energy, and the bottom row is a wavelength energy. And what you're seeing here is, let's see, the first two, I think, yes, okay. So the first column, that is the actual image that was taken of this host galaxy after this GRB went off. The second column, I believe, is the image of the host galaxy archival data. So data from a long time ago, from a while ago, where there was no GRB. And so what you do is you take your first image, subtract out the image of the host galaxy, and you get your third image. What's left behind should be the kilonova, or whatever is causing the optical excess. And what you're seeing here is that when you look at shorter wavelengths, and so this is, I think, corresponding to the blue curve on the right. When you look at shorter wavelengths, there's really nothing there. There's sort of a lot of background fluctuations, but you don't see a bright spot over there. When you look at the slightly longer wavelength, so now this is the red that's plotted over here on the right side. When you look at the red, there's something that's left behind. And so there's something that's left behind there, excess there that's showing up at red and not at blue. And this is saying was the kilonova in this case. Seeing here on the right, so we see the data points and what the slope lines are what you'd expect if things were just regular afterglow. And then you see this little bump, and what you're seeing, the orange is sort of a rough fit to what the kilonova might look like at the time. And then there's is this neutron star, or neutron star black hole? And because this just had a data point. If it just has one data point, how can you tell? And so basically, this just shows that this is consistent with both neutron star, and neutron star black hole. The questions, right? So we've heard a little bit about 1708-17, so the kilonova associated with the merger of two neutron stars, the binary merger. So if you ask people, it's easiest to model that or explain that with two neutron stars merging. You could also explain that with a neutron star black hole. You could also go a little bit more exotic and say neutron and a boson like matter, a little bit more exotic. And so this is, you want to be absolutely precise. Even if you believe saying that it's necessarily, so the binary merger did not have two neutron stars, that's fine. Even if you say it was two neutron stars, that doesn't mean every short or every kilonova comes from two neutron stars. There could be some that come from two neutron stars, some that come from neutron star black holes. And so the questions that we're going to be asking in the future in the field, once we get more data, does it look like all kilonova come from what type of Does it look like they come from the type of events and things like that? There was also a while, I think, when we thought gamma ray bursts could also come from dwarf mergers. And I think that's not entirely out yet. There could be sort of GRBs that come from white dwarf black hole. Was on something else going on there. Yeah, I think that's it for this. Are any astronomy questions like what's a color? Probably doesn't. I heard that radio. No? Radioscopes? Yep. Yeah, sure. Yeah. So after this, the binary neutron star merger and the related GRB, after this has happened, have there been any changes in sort of procedure when a short GRB like this happens? The answer is kind of yes and no. The problem is a lot of this politics. It's not necessarily right. This is being done by people. Science is being done. People have their own preferences. So a lot of what it comes to is not necessarily what produces the best science, but also a little bit of politics. There is a little bit of what produces the best science. One thing that I think people are working on, I'll talk a little bit more about this later, I think. Doesn't matter. So what happened with 17 is Fermi, so the GBM, the gamma ray burst monitor, was just a wide field burst monitor detected the GBM, and it was very dim. It was relatively dim, so it didn't really do much, but it just sent out an automated notice and said, here's a GRB right here. LIGO then, the two did sign, that was similar, or a signal that was consistent with coming from the merger of two events. The problem is the GBM Fermi gamma ray burst monitor cannot localize very well. It's just a detect rates, and they're pointed at all different parts of the sky. So something that comes from over there, the detectors pointed over here are going to see higher rates. The detectors pointed over here are going to see lower rates. But that's all it can do to try to localize on the sky, and that means the GBM, for instance, can only localize things to a wide circle. LIGO has a similar issue where when LIGO detects something, it detects the gravitational waves, and based on, you have your detection responds to things moving, and or responds to gravitational waves from different parts of the sky. So came from that part of the sky. But all of that is still, let's see, the LIGO error circles can be thousands of square degrees in the sky. The GBM ones can also be thousands of square degrees. It can get better. It can do hundreds of degrees. That's still not good enough for your X-ray optical detectors that need like less than 1 degree, much less than 1 square degree on the sky. And so what you need to do then is to be able to try to. So what happened? LIGO error contour, they're elongated, they're like that. There's a big difference between if your GBM error contour is over here, which doesn't give you any new information, versus if it's over here, or like sort of in part of the sky, right? Which kind of tells the optical telescopes to, okay, maybe look in this direction a little bit, focus over here, don't focus over there. And so one thing that people are working on is trying to get this GBM, this improved GBM localization down to calculate. I think that's one thing, is that we're trying to get better localizations and to get them faster. Yeah, and the next LIGO is turning on. Keep saying LIGO. I apologize to Virgo people. So the next LIGO observing run is going to start early next year, and at that point, everything is going to be public. So all the nodes are going to be public. It's also exciting because if you have a telescope, let's say, even just a backyard telescope or something like that, or if you know someone who does. So the kilonova that was associated with the binary neutron star merger, that was individuals, amateur astronomers, theoretically it as well. And so if you have a telescope or you know someone who has their own telescope, it might be interesting to keep an eye on the GCs to get an idea of where things are. And if one of these really fancy, I think the kilonovas that over there, look over there, and if all astronomers look at that part of the sky as well, then you can also get that data point, basically, how bright is the kilonova at this point. And your own telescope, you can see the kilonova, you can sort of add on to the information that's there, right? Because at early times, things are changing very quickly. And so it's really important to get enough data at early times or as fast enough as possible. And so that's kind of exciting. Have your own telescope, you can actually be part of this. All right, that's it. And we'll see you guys again in, I don't know, how long is coffee break? Okay, see you guys again in half an hour, or one of us will see you again. Oh, sorry that, yeah.
No, it was. I'm wondering. Because I expect more physical intuition that Gammarays burst low frequency, but at some point you have events.
Yeah, so
That will give me an estimate how old is the whole galaxy or something like that. I'm not sure.
yeah, where did I put this? This one. This,
Exactly.
right? Yeah, so this is the
So,
network.
for example, here I have Redshifts, really old galaxies.
Yeah. So part of the problem here is that it's hard to draw really firm conclusions from this sort of thing because, again, it's a problem of observational bias versus what's intrinsically there. So part of the problem is that galaxies at different redshifts in general look different. So galaxies that are really far away, the lights are only reaching us now, and so we're basically seeing the galaxy when it was much younger, earlier in the universe. So if the galaxies were much earlier in the universe, things look very different in the early universe, right? So in general, in the early universe, so this goes back to sort of, in the early universe, basically, you could have heavier stars. If you could have heavier stars, then you could maybe have more massive, you have more massive stars, and so you could have more gamma ray bursts, right? And so it's possible that the GRBs that come from over here are intrinsically different, maybe from the GRBs that come from over here. So there's that little bit of a confounding factor there as well.
So it will depend on how the stars are developed.
Yeah. Element, yeah.
I don't know.
No, but
I don't know what kind of intuition you could have there, like a higher rate structure.
Yeah, but I think this is a good question though, because a lot of times, so there are two ways we do GRB science, right? Sometimes we just look at individual GRBs and we say, what can we learn from this one GRB, like the recent GRB. But a lot of times, what we do is we look at GRBs as a whole, as a population. So there's population studies. So that's good thinking because it could be that just from looking at this distribution and by working backwards and saying, all right, what are some assumptions I can make about how stars back then look compared to stars now, or galaxies back then and galaxies now? Can I say something about?
Like why you have a lot of events, low redshift.
Yeah. Well, yeah. So part of the other problem though is that, right? So GRBs, they're bright, but at some point they're still not bright enough for us.
You need to wait until the stars behave, evolve properly, like get old enough.
Yeah, exactly. You have to wait. Yeah. Exactly. You have to have the star. Yeah, right, because the star has to collapse in the first place. The jet has to be pointed at us for us to see it. So there's that as well. So the actual number is going to be much different. And then it has to be close enough for us to see it, for us to observe it. If it's too far away, we also have to observe it.
there's a lot of factors in there. But it could be that by looking at, I mean, no, that's good thinking though, because it could be that just by putting all these factors together and working backwards from the data set, you might be able to tease out something interesting about the underlying distribution. And so that's also something that we do with geoinference, is trying to do these population studies, saying with these assumptions, what can we say about the distribution?
So a good approximation is just study the log redshift.
Yeah. The other problem. Oh, so also interesting. The other problem is, I think there's two factors here, right? So one is that, all right, if it's too far away, we won't detect it because it's too big. But the other thing is that, so let's see. So this, okay, redshift basically is distance, right? But